want to derive the prediction over the test labels given in the test distribution given the inputs. So by Bayes' rule, you can just check this on a napkin after the talk. It's basically how likely is this joint combination in the source distribution. So this is just a discriminative classifier you can fit on the source distribution. And then this term downstairs is a constant, right, independent of y, so we'll ignore it. And then we've got two other terms. This is just the prior probability of each combination in the source, and this is the prior probability of each combination in the target, right? So this is a discriminative model we can fit. We can estimate the priors in the source just by counting because we have labeled data. So there's only one thing left to do, and that's to estimate this term here, this Q of YZ. And this might have changed. The whole point is that the joint of Q of YZ might be different than P of YZ, right? Because the distribution of males and females is different. And we don't get the labels. A patient walks in, and when the machine isn't told what sex they are. Okay, so how are we going to estimate this term in pink? If we can estimate this term in pink, then we can just plug it into this equation, and we're done. Okay? And if our assumptions are correct, then this will be the optimal thing to do. So how do we estimate this term in pink? Well, we can group these y and z variables together into a single variable. I was calling it m earlier. And if you squint, hopefully you've had enough classical training that you say, oh, this kind of looks like a mixture model. I got a discrete latent variable, and it's generating the data. And I didn't explicitly fit a generative model of x given m, but I can derive it by inverting my classifier, right? Which is on the, which follows from this equation here. So I know how to fit mixture models. This likelihood term is constant because it's the same in source and target. So all I have to do is update my prior. So I can just run EM, and all I'm doing is estimating the prior, and that's just the table of 4 numbers if it's binary, right? So it's super easy. You need very little data. It's very little time. And you can actually prove, as it's been proved in prior publications, this objective is convex, so it'll find the global optimum. So you don't even need to use EM. You could use something else. The EM is nice and simple. Okay, so that I'm not going to sure you've all seen EM for mixtures of Gaussians. It's basically the same, except we're just updating the prior term by normalizing the soft counts. All right, so that's it. You fit your supervised model on the source. You run EM on the target. You update your weights and apply a model, and that's the whole pipeline. So let's evaluate its performance. So we're going to take the colored MNIST data set as a warm-up task. So the task is to predict whether it's an 8 or a 9. It's a binary problem. And there's a background variable, which is red or green. And in the source, red is correlated with 9s. And when you shift, then red becomes more correlated with 8s. And the degree of correlation is on the horizontal axis here. So 0.5 means they're uncorrelated, like the color has nothing to do with the class. So we train on a highly skewed distribution similar to before, 0.1. So 90% of the reds are 9s, right? And we can fit our model. And if we apply that model to the different test distributions, the performance drops a lot, as we showed before. That's the black line. That's your baseline empirical risk minimization approach. Another thing you could do is to do group robust optimization, and that gives you this flat line. So it's robust to the variations in the distribution as it's supposed to be, right? It's invariant to the changes because you optimized over all possible changes. So you get a flat performance curve. And that's typical for like a minimax kind of approach. But we are the curve in blue, which is the Bayesian approach, which is adaptive rather than minimax. And what happens is if there's a signal, if there is correlation between the hidden label and the target, then the model picks up on it and exploits it to do better than an invariant method. So you can see the blue curve is above the invariant method when there is some signal. And when there is no correlation, like at 0.5, it touches it. So it's strictly superior to the invariant approach. Okay, so that's on this toy data set. And then we applied it to the medical imaging data I mentioned earlier, the chest X-ray data set, and get basically the same results. And here we applied it either to a neural network or to a linear model, like logistic regression on top of embeddings. And we also applied it to random forests, just to prove the point that it's not specific to neural networks. Unlike a lot of methods in this space are like sort of hacks that only work for neural nets and might only work for images as well. And like this is a black box technique that will work for anything. Okay, so we're optimizing the average performance, but you can also get group performance out of it, like to minimize worst case performance. And there we just match prior art, we don't beat it, because we weren't trying to optimize for that. And then I'll go over this briefly. Well, I did assume all the metadata labels, these Z's, were available, but it turns out you only need a tiny fraction, and then you can just impute the rest. So you don't need a lot of strongly labeled data. You can ask me about that later. Okay, so I want to wrap this first part up. This is just pillar one. Don't worry, not all the pillars will be this deep. So there's some obvious next steps on this project, and if you're interested in this kind of stuff, come talk to me. There's a recent paper called Spurious that just came out recently, where they actually artificially create a synthetic data set by using generative models to control the factors, and it's a very challenging benchmark. But I think it'd be great to like throw the algorithm I described at this benchmark and see how it does. And then there's also like more theoretical questions about what could you do if you wanted to do unsupervised learning of the factors of variation that are changing between source and distribution. And I think you need to take into account identifiability for that to work well. So I think that's sort of an open theoretical question that's interesting to work on. But I think this experimental question is sort of low-hanging fruit, relatively low-hanging fruit. And if you want to get into this space and you're interested, come talk to me. Okay, so just to pop up a level, this is pillar one, predictive modeling. I said it like, it's 99% accurate, except when the world changes, which it always does, and then it's sort of arbitrarily bad, so you need to be robust or adaptive, right? That's basically what I've been saying for the last few minutes. I think this is a very prevalent problem. This is a whole bunch of data sets from the WILDS data set at Stanford to do with medical imaging or satellite image analysis or text classification. And as the distribution shifts between different populations and locations, then performance can drop. And I'm not saying the approach I described is just one of many possible ways of handling shift. There's a lot of ways in which the world can shift and change. So we need a lot of different techniques to capture the kinds of variations that you see in real data. And I think causality plays a role here because you want to identify things that are stable with respect to interventions or changes in the world and things that might change. And just one last word on this topic. It's sort of tempting to say, oh, all we have to do is like scale, train a bigger model, use more data, and then it'll all work better. And in fact, on standard benchmarks, big models and big data do in fact work better than small models and small data. And they sort of saturate. So people say, oh, you just need to pre-train on the whole internet, and then you're done. But that's just not true in general, right? Because there's a long tail of possible failure cases. The world is actually quite diverse, and not everything is on the internet. And so you can't expect a model that like absorbs the whole internet to do well on arbitrarily new situations. So here's a fun example that came out recently. I saw it on Twitter. So this is a giraffe, that was born in a zoo in Tennessee, and it was born without any spots. And so someone took one of these state-of-the-art image generative question answering models and asked it to sort of describe this image and say if there's anything unusual about it. And they could not make the system say, oh, this is kind of weird, it's a giraffe, but it doesn't have spots. Like, he prompted it in many ways, and it just couldn't. It's never seen a giraffe without spots. It's out of distribution, and it doesn't matter how much internet data you've trained on, it will not, at least with the current technology, it will not detect this anomaly. So, like, there are lots of success cases, but there's a long tail of failure cases as well. And that's where I think, the interesting research questions are. And also important for practice, because we want things to not fail arbitrarily when the world changes. All right. So that was pillar one. I can take a question or two if somebody has any before I move on. Yes? Yeah, I heard you. Yeah. So the question is, it might be important to detect if a test sample is from a new distribution or not, as opposed to just adapting. So yeah, you can, if Indeed, right. If it's the same, you can just deploy your current model and you can be confident that it will work. Detecting if a single sample is from a new distribution is difficult. If you get a batch, then you can do a standard distribution test. And if the world has changed, then you can update your model, hopefully, either with labels or without. So yes, you can try to be, you can have sort of a certification about whether it's working or not. And if you don't think, if the world has changed, you can either update the model or you can pre-train it to be robust. So there's many approaches you can take. Yeah. Any more? No, okay, all right. So let's move on to decisions. So this is section 6 of my book. One more question. I can't really see because of the lights. Do you want to just shout out because I can't see you, I'm sorry. Oh, the mic's coming.
So thank you for the first part. I actually have 2 questions. I'll start by this. So in your talk, you assume that the data generation, for instance, process might be identical. But I'm wondering how realistic this is to, for instance, in practice, discover the true causal graph, because sometimes it's also important, like for the inference aspect. I wrote my question before this slide, so I don't know if you are going to answer. It was about the predictions and like the domain shift thing you discussed about. Some causality works, for instance, have been working on building invariant models. So for instance, they can use content style. So for instance, in the example of the cow you gave, the content will be, for instance, the cow, and the style which is changing will be the grass or the background, anything. And there's also about the chest X-ray example you gave. There are also some work, for instance, who are defining, for instance, we train on the data on one hospital, so that's one domain. Then we want to move to another domain, so another hospital. They try to model this problem as, for instance, new domain is equal to old domain plus some variation. So instead of actually working on an entire data set, they try to learn some representation or some causal aspect of the new data that might explain and like synthesize the new conditions that are inserted, and then you only actually learn to adapt to that. So maybe you will answer this in this part, but I was wondering what are your thoughts, because what you talked is quite related to that and also very true probabilistic.
I'm not going to talk more about distribution shift. Actually, that was, so I should have flagged this at the beginning. I have 4 pillars, and for each pillar I have a little example. This is a big example, but there are many approaches to the problem. It's a multi-dimensional problem, right? So the domain invariance that you talked about is a different approach where you learn a representation that's invariant across, if you have multiple training domains. The setup, so there are different problem settings, right? You might have different environments at training time, and then you get one at test and you're not allowed to adapt. In what I talked about, there's one source distribution and there's only one target distribution, but you get unlabeled samples from it and you're allowed to change your model, right? That's not always feasible. If you get labeled data from the target distribution, then you can just do, continual fine-tuning. I'll talk about that in a minute, actually. So there's many ways of specifying the problem. So you're right. I just described one possible approach, right? It's a drop in the bucket. I talk about some of the others in one of the book chapters, but it's a big space. Okay, so I'm going to move on. So I've talked about predictive modeling where you predict the distribution of outputs, right? But ultimately, we want to go beyond predictions and make decisions. And predicting the most probable class is a form of decision making, but there are other forms of decision making that might be more suitable. So that's a special case. Classification is a special case of decision making. So the general setting, here's Bayesian decision theory 101 in one slide. And I'm just introducing this to explain notation and I'll flesh it out. So the setup is the following. nature has some state that we don't see, this H. And we don't get to see the world, but we get some data that comes from the world, and that's what we'll call the observation O. And I'm a decision maker or an agent, and I have a policy that tells me what action I should take for every possible observation that I observe. And how am I going to choose the action? What should I do? Well, in decision theory, you specify a loss function that tells me how much loss I will incur if I take action A in state H. Okay? So how do I choose what to do? What's the optimal policy? Well, the optimal policy is the one that minimizes the posterior expected loss, if you're a Bayesian. So what is that? That just says, well, it's the loss I would incur if I performed action H in each state H. I don't know H, so I'm going to average it out with respect to my beliefs about H, given the data O. That's the posterior, right? Or equivalently, we can maximize expected utility, which is what economists do. But it's the same thing, modulo sign. Okay, so that's the basic principle. This is called the maximum expected utility principle. It's the foundation of all rational decision making. So the key questions are going to be, what's the form of the model that we use to compute these probabilities? What's the form of the loss function? What's the nature of the latent states? What's the nature of the actions? And by varying all of those dimensions, you can span all four pillars. That's sort of that is the grand unifying theory here. Okay, so let's just do some examples. So classification is a simple, or predictive modeling more generally is a simple case, where this is the equation from the previous slide. So in the new notation, the action is to predict y hat, it's the output, that's an action. And my policy is a predictive function, f. Sometimes in decision theory it's denoted by pi, but in predictive modeling it's denoted by f usually. And what should I do? I should predict the label that minimizes the posterior expected loss given the input x, but also given my training data, right? So that's the optimal predictor. Okay, so let's flesh that out some more. So if you're doing regression, it's reasonable to use L2 loss, squared error. And in that case, the optimal action is the posterior mean. And if you're doing classification, it's reasonable to use 0-1 error. And in that case, the optimal action is the most probable label, the map label. Okay, so you all know this. This is, very intuitive and elegant, I think. But the cool thing is you can go beyond just standard classification and regression, and you can expand your action space. So this is somewhat related to the question the woman in the front was asking. So you might get some data, and you might not know if it's class 0 or class 1. And you can say, instead of always predicting one of the classes, you can say, I don't know, I refuse to classify, right? This is called the reject action for historical reasons. So you can see in this picture here in the middle, if the probability assigned to either of the classes is sufficiently low, then you're better off like refusing to make a prediction that's wrong. And how do you decide when you should say, I don't know? Well, it depends on the costs of the relative actions, of the errors that you might make, right? So if you predict, suppose your action is to predict some action A, you predict the true label Y star, then you'll get no loss, right? Because you did the right thing. Suppose you predict an incorrect label, you're going to get an error, lambda E, we'll call it, some number, right? You get punished $100. Now, suppose you're lazy and you say, I don't know, I'm going to refuse to classify, right? So I pick the reject action. I'm going to charge you $1,000 for that. So then you can just do some algebra and figure out when should you decide to refuse to classify. And you get this result, which is quite intuitive, which says, look at the probability of the most probable class, and if it's bigger than this ratio, then predict it, otherwise refuse to classify. And that will minimize your expected loss. So this is kind of cool, right? So if you don't think that the data belongs, if your model is not very confident in its output, then you can just say, I don't know, and then a human expert can come in and hopefully save the day. So this is an example of something you can do with decision theory that you can't do with vanilla predictive modeling. And you can extend this to like active learning and Bayesian optimization and all kinds of sensor placement and all kinds of things where you need to perform information gathering. And then you can do that in an iterative loop, right? And that gets you into sequential decision theory, which is the foundation of reinforcement learning. So this is like a ridiculously large field. So I'm just going to give you like a little taste. But the idea is now it's the same as before, except you take an action, incur a loss, and then you repeat. So you do something, and then you realize you maybe regret your action or you don't, and then you get more data and you have to take another action, and you keep repeating. And now the goal is to pick a sequence of actions that minimizes the posterior expected loss over the sequence, where the posterior is with respect to the distribution over possible actions that, losses that you might incur as you act in the world, or rewards that you might incur, right, if we flip the sign. Okay, so this sequential decision theory is like an extremely general framework. I mean, you can argue that all of AI is a form of sequential decision theory. And so it's like too general for me to cover in 15 minutes, or whatever I've allocated to this pillar. So I'm going to look at a special case that's simpler, but still quite important, and that's called contextual bandits. And basically, the setup is shown in this diagram. So the idea is the same as before, but I'm going to take a sequence of actions, and the world is going to give me a sequence of states. But I'm going to assume that my actions have no impact on the state. So the world just like presents me some data, and I have to react, and I get a reward. And then it presents me something else, and I have to react, and I get a reward, and so on and so forth. So the data just comes at me, but I don't affect the data stream. So as an example, suppose I'm Google, and I'm serving ads. And you type in a search query, and I'm allowed to show you 5 ads. And I want to show you, I have to choose which ads to show you, right? I've got, a catalog of 5 million. I get to pick 5 of them. And I want to show you an ad that you're going to click on so that you're happy, you find the thing that you're looking for. And the advertiser's happy because they make some money, and Google's happy because they also make some money. So this is a common application of bandits, right? So the query, the search query, is coming from the user. You can think of that as the state of the world. Like every user signs up with Google and asks some random question. So I don't try to model it, it's just a random process. And my action is to pick an ad, which is like one of n possible things from my list of ads. And then I present the ad, and then you either click on it or not. And then if you do, then I get some reward. Google gets some reward. And if you don't click on it, there's no reward, right? So contextual bandits are like super widely used in the tech industry for recommendation systems of ads and of Netflix movies and Amazon shopping and whatnot. But they're also used in many other applications. So they're used in clinical trials. They're used in, what else do I have here? It's Bayesian optimization is like an infinite version of this. So it's a very broad model class, but it's not as broad as all of RL. Okay. So you can think of the actions that do I have a little picture? Did I miss my picture? Yeah. So you can think of the actions that the agent performs. Let's suppose there's a finite number of actions. These are traditionally called arms. And this setup is called a multi-arm bandit. So a bandit, if you go to a casino and you play the slot machine, that's called a one-arm bandit. You pull the handle, and you may or may not make money, right? So now imagine a casino which has a whole bunch of slot machines, and each one pays out money at a different rate, and you don't know the rate at which it's going to pay out. You don't know which one's the lucky machine, right? So you could like pull each of the arms until you find one that wins, and suppose you find one that gives you, $1. What should you do? Well, you could pull it again, but maybe it only pays off 50% of the time. You just got lucky. Maybe there's some other machine that pays off 80% of the time, but you haven't found it yet. Right? So you face this dilemma where you need to explore all of the arms or all of the actions to figure out which ones are good. But if they're stochastic, you might need to do that many times. So you face this problem, which is called the exploration-exploitation trade-off. So if you know what the right thing to do is, then you should exploit your knowledge and keep doing it, and you'll maximize reward. But when you're in this interactive setting, you don't know which things are the right things to do, right? You don't know the reward function. You're trying to learn it. So that requires exploration. That requires that you do something new because you might like it better, right? So here's a little cartoon. You're some robot, and you could go to your favorite restaurant, and you'll be pretty happy. But there's this new restaurant, and I don't know, should you take a chance? Maybe it's better. You have to try it and see. This is a fundamental tension that arises in online decision-making. Okay, so this is a super well-studied problem, and of course there are standard solutions to this problem. So one of them, which is quite simple, but also theoretically well-grounded, is called the UCB heuristic, upper confidence bound. So the idea is the following. You're going to learn a model that predicts the average reward, mu of A, for each possible action A. So I play the slot machine, and I say, this machine pays off 80% of the time, this machine pays off 50% of the time, this one pays off 10% of the time. Okay, but I've only played with these machines a few times, right? Because every time I play, it costs money. So I'm not very certain. So I'm going to also model the uncertainty in terms of the variance of the output of the rewards that I see. And I'm going to use a heuristic called optimism in the face of uncertainty. So I see a machine, I'm not really sure if it's going to pay off or not. So I'm going to assume that the reward I'm going to get is equal to the mean plus some upper bound on the confidence. So I'm going to assume that the reward I get is the average reward plus some inflation factor times the standard deviation. So I'm being optimistic that it might pay more, like the best possible thing I think it could do. And that will encourage me to explore new things, right? Because if the uncertainty is large, because I haven't explored this arm very much, then I'm going to assume it's a good thing, and I'm going to explore the world quite widely. And then when I explore, I'm going to get data, and my uncertainty will reduce, because when you learn about the world with data, then your uncertainty goes down, right? So then it will naturally concentrate on the thing that is the best, with the highest expected reward. So this heuristic will automatically trade off exploration for exploitation. And you can prove that it's optimal under certain settings. But to make it work, the key thing is we're going to need not just a predictive model of the output, a model of the uncertainty as well. And we also need to update that model online. There's another approach you can use called Thompson sampling that I think I'm going to skip. But it's similar. Like you maintain a distribution over outputs, and then you sample one possible output from your belief state, and then you optimize greedily with respect to that. So it's a little less intuitive why that works, but it's simpler computationally. But the idea is similar, that you need a distribution over your outputs, and you need to update it. Okay. All right. So how are we going to tackle this problem? So it's basically another predictive modeling problem with the decision making in the loop. So you predict and act, but at each step, the data comes in one by one, and you get to control the data, right, based on your actions. So you want to be able to update your model very quickly. And you want to maintain uncertainty so you can do this exploitation trade-off stuff. So we're going to be Bayesian, because that's a very natural way to model uncertainty. And if your model is a linear model, like this one, then everything can be done analytically in closed form, and life is beautiful. So here I'm saying that the probability of the reward for each possible state or context and action, I'm going to assume that it's a linear model. So for every possible arm, I have a different parameter vector, theta, and it's a linear function of the state with some, let's say, shared variance. And I want to learn these parameters theta, maybe sigma as well, okay? So the distribution over theta, I'm going to assume all the arms have independent rewards, so that factorizes into a distribution over parameters for each arm separately. And then if I make the assumption that my distributions are all Gaussian, since the model is linear, then the prior is Gaussian, the likelihood is linear Gaussian, the posterior is also Gaussian, and you can look it up. It's like equation, I don't know, 6.23 in my book. And you just plug it in. It's like one line of Python. And you start with a mean and variance, and then you plug in the data, and you get a new mean and variance out for every possible arm, right? So this is called conjugate updating, and it's very elegant and beautiful. It's a little bit of algebra to derive, so I'm not going to do it now. But this is classical stuff, right? So this is all well and good, and this is optimal. If your model is, if the world really is a linear regression model, then you can't do better than this. But of course, the world usually isn't well modeled by a linear model, so we want to replace the linear model with a nonlinear model, such as a neural network or a decision tree or whatever. So this is again going to be similar to the predictive stuff in pillar 1, except we want to not just estimate a point estimate of the parameters using SGD, but we want to maintain uncertainty over those parameters so we can do decision making. So we're going to, once again, make a Gaussian assumption about our beliefs, our distributions. And now the million-dollar question is, how do we do updating of this belief state when it's nonlinear? Okay, so this gets us into non-linear but Gaussian Bayesian modeling. So this is a well-studied problem, and there are standard techniques for this as well. So what we do is we build on a technique that goes back to the 60s called extended Kalman filtering. And the idea is the following. So we're going to model our parameters as belonging to a state space model that evolves over time. So these are the unknown weights of our bandit, or it could be just a regression model. And they evolve over time. Either they could be constant, like zero variance, or they could have a random walk model or some other model. And then we get to observe some output, which is generated by our parameters in the input features X or S. Okay? So here I'm assuming that the likelihood is a nonlinear model, either a regression model or a classification model. And I want to do Bayesian inference over the parameters as the data streams in, right? So I'm going to alternate. I take an action, I get a reward, I update my model, and I repeat. And what I'm talking about now is how to do the model updating, because the action selection is done with UCB. Okay, so I can't show the video because this is a PDF file, but there is a video here which is cool. You can see it later, which visualizes like data streaming in one by one, and then this EKF algorithm. I haven't explained how it works, but do I have it? The EKF algorithm, what it does is it linearizes the model at every step, and then it performs that closed form update that I just described, and then repeats. So this is classical stuff. And you can apply it to learn neural networks online as the data streams in. And this was proposed way back in 1989. So this is very cool. Actually, let me just see. I'm going to skip ahead for a second. Okay, let me show you why it's cool, and then I'll explain the problem and the solution. So let's look at a simple example where we're just going to do classification online. So there's no actions anymore. Just labels stream in. It's just like a special case of a bandit. Then we'll do it in 2D, so we can make plots, right? So it's a binary classification problem, 2 moons. I'm sure you've all seen this, right? So imagine that you get one labeled data point at a time, and the data just streams at you, right? And you've got to act, preferably as fast as possible. So if you run this EKF algorithm, then after 200 steps or whatever, you've got the decision boundary, and it's like optimal, basically. What happens if you run gradient descent as the data streams in? It's pretty crappy, actually. You can see here, this is like online gradient descent, even if you tune the step size. And the problem is it's memoryless, right? It has the current parameter vector, but it doesn't model the correlation between the different dimensions. So you need to keep past data, or you need to see the data many times. So if you can afford, in the batch setting, so most machine learning is done offline, right? You suck the whole internet down into your hard drive, if you're Google, and then you train on it for 3 months, and then you release that model to the world, or not. You have a frozen model. But if the data is streaming at you continuously, then if you try to keep up using gradient descent, it doesn't work so well. If you can afford to keep the past data and revisit it, then you'll get a good result. But by using these Bayesian methods, we can do it fully online, and essentially the probability distribution stores the memory of the past, so you don't need to store the data itself. So it's kind of cool, and you can do it, you can compare it to standard online gradient descent is in green. You can do the replay SGD is in dark green, and then the method I'm going to tell you about in a minute, which is some common filtering variant, is in blue, and it makes the error go down much faster. And you can apply it to non-stationary problems as well. And let me just get to the punchline, and then I'll tell you the method. You can apply it to bandits, of course, which is how I motivated this in the first place. And the Bayesian method does much better than like a linear approximation or some plug-in approximation based on SGD. Okay, so this is cool. Bayes is wonderful, but it's expensive. So even this extended Kalman filtering algorithm, which is a fairly efficient algorithm, is cubic in the complexity in the number of parameters, because you have to perform a matrix inversion. So we have a paper that was presented last week, actually, at the Collis conference in Montreal. And it uses a very simple idea. And it says, okay, we can't afford to store this full Gaussian because it has a d by d covariance matrix. So let's just approximate it as diagonal plus low rank. And we get to choose the rank depending on our computational budget. And if we set the rank to 0, we have a fully diagonal approximation. And that doesn't work very well because it ignores correlation, and it's no better than gradient descent. So you need to model some of the correlation. You can't model all of it because it's too expensive. So diagonal plus low rank is a common approximation for Gaussians that has been studied in prior work. But prior work chooses the optimal DLR approximation using stochastic variational inference. There's kind of high variance. So what we did in this work is to borrow the trick from EKF. So we linearize the model at each step, and then you can compute the DLR approximation analytically. You do a closed form update, and then you do an SVD computation. So basically, the whole algorithm reduces to this. So you start with a prior precision matrix that, by assumption, is diagonal plus low rank. You observe some data. So you absorb the data through the linearized model. You update the mean using the Kalman gain matrix. And then so this is now exact according to the one step. But when you did this Bayesian conditioning on the new data, you're no longer rank L, you're like rank L plus C, which is too expensive, so then you project it back down using SVD, and then you repeat. So it's fully deterministic, it's quite fast, and it works well, as I already showed you in all these plots. So anyway, so that's a cool trick. Okay, so let me just pop up a level. That was like a deep dive into one thing you can do in this pillar 2. But like more generally, I think decision making under uncertainty is a very interesting area and needs probabilistic models. And it's very useful for things whenever you don't have a lot of data, so you're in the small data setting, so you might have a lot of uncertainty, or you're in the setting where you can choose the data, right? You're doing active learning, or you're doing bandits, or you're doing reinforcement learning, or experiment design, or sensor placement for environmental modeling, or whatever it is, right? Or you want to choose what experiment to do next in the lab. All of these settings where data is expensive, this kind of machinery is useful. So I just want to have a shout out to a couple of things coming up later in the week. So on Monday, Randani Muva, I don't know if he's in the audience, is going to give a talk about probabilistic modeling for climate and modeling uncertainty in climate models, which is very important. And then I'm actually giving us a little 5-minute spotlight on Thursday as part of this Google mentorship thing about a project on Bayesian neural networks and extrapolation with uncertainty bound. So if you're interested in this kind of Bayesian stuff and you want to like get your hands dirty with a project, come to the spotlight and then talk to me. Okay. All right. I will take questions on decision theory if there are any before we move on. Yes. So, go ahead. Oh, you want the mic?
Sorry, it's me again. So the thing with UCB is that you described, like that we can use that acquisition function. It works well, and sometimes like it favors like exploration and diversity depending on the task. But I was wondering if, based on your experience, you have any like heuristic or like you are aware of any work that actually learns to pick efficiently that coefficient, like you have the mean of the model plus something, the uncertainty. And you also didn't talk about other approaches like maybe expected improvement, all those type of things and how they compare. The second thing is a question, is a suggestion, I don't know if it's valid, but about the next slide about the update. Do you think it would make sense, for instance, to try to build a neural network that actually learns to predict the mean and the standard deviation of this distribution. And then we use that actually to perform the update. Because those are, in my opinion, two of the main parameters. And then we leverage them across the state, the reward, and the actions.
Yeah, sure. So let me reiterate your question. So the first one was basically, how do we choose the C parameter?
Yes.
Yeah, so I haven't studied that. I'm sure it has been studied. It's sort of a degree of optimism, essentially. Actually, in our experiments, we didn't use UCB. We used Thompson sampling, where like the analogous thing to C is like the variance, and we estimate that with Bayes as well. And then, so what's the value of your uncertainty? That depends on the prior that you use. And we didn't really study that. Basically, the contribution of this work was more, the second thing was this updating in the nonlinear setting, right? We just plugged that into an off-the-shelf decision-making heuristic, like either UCB or Thompson. We didn't try to innovate on the decision-making side, but you are right that there are other heuristics that people use, like expected improvement and whatnot. And you know, you can actually write down the optimal thing, but it's generally intractable. So that's in terms of how you convert your beliefs into decisions, so there's room to explore there. In terms of computing the beliefs and updating the beliefs, so your second question was, can you learn a neural network to basically do Bayes rule? And yes, you can, and that's like meta-learning. So if you have a set of distributions that are related, you could obviously apply Bayes rule and then basically amortize it into a neural network and like learn to emulate what Bayes would tell you. But you could also more directly like learn some function that, or some state transform in an RNN or a transform or whatever that's opaque, you don't know what it means, and then it's used in your policy, and this is the kind of thing that people do in RL. So you can do that. It's super expensive, computationally and statistically. So it's usually done like offline meta-learning, needs like tons of data and related distributions. But then once you've trained it, then it's very fast. So, you know, there are different solution techniques that meet different goals depending on what you're willing to assume, right? So here we're assuming a linear model, which is obviously pretty strong. Here it's a nonlinear model. This could be any neural network, but you know, we're making Gaussian assumptions and so on. So, you know, there's always caveats. Yeah, if there's a problem that you're going to repeatedly revisit many times, then you might want to amortize the cost of this update procedure, and then you can train a neural net to do it. But then you don't get this beautiful like Bayesian updating stuff. So I'm partly a hammer looking in search of a nail. Like it's kind of fun to drive all the math and not just use a neural net to drive the math for you. But it can be more sample efficient too. Okay, let me move on to part 3. I'm watching the clock. Okay, so I've talked about predictive modeling, supervised learning, and decision making, and that's all dealing with data, right? You have observed data X and outputs Y or actions A, and you're living in data space. And you know, your performance can be measured in terms of the data in data space. But there are other problems, especially in the sciences, where you're not really, you're given data, but what you're interested in is what's behind the data. What caused the data? What does the data mean, right? And that's what I call analysis, like data analysis. So this is, so in classical statistics, this is like the bread and butter of what they do, right? They don't so much focus on predictive modeling. They focus on choosing a model that might mean something for their domain. So it might be a linear model, it might be a nonlinear model, it might be a physics-based model. And then they just fit it, they have some data, and then they fit it somehow. And then they just stare at the parameters of that model, and they read the tea leaves and make conclusions about the world based on the model fit, right? So this is standard statistics, which I think of as a subset of machine learning. And if you do the Bayesian approach, there's like tons of great books on this. And this also is useful for like causal effect estimation and things like that. But one of the focuses of statistics is not just estimating parameters, but modeling uncertainty about your parameter estimates, right? So that's visualized in this little plot here. So we've got like some empirical number of diseases across different populations. So you can get a point estimate by just dividing the number of positives by the size of the group, right? So this is like n1 over n0, or over. So this is the empirical count. That gives you a point estimate, but some of these sample sizes are quite small, so there might be some uncertainty. So you might want to do a fancy hierarchical Bayesian model to model your uncertainty. And then the bottom line is you get a point estimate, but you also get error bars. And you could do this with frequentist methods too, right? I'm just by inclination a Bayesian. But the output is more or less the same. It's a set of parameters with some notion of uncertainty. And if your model is meaningful, then you can sort of, it's legitimate to like read the tea leaves. If your model is like a linear model that doesn't fit, then this is totally bogus. And this is what, what's his name, made this point. The two cultures. Leo Breiman. There's a very famous paper by Leo Breiman, who was a professor at UC Berkeley, invented random forests and other stuff. And he said basically all of classical statistics is kind of bogus because they fit models that are very simple, and then they try to interpret the coefficients of their linear regression as meaning that A causes B. And he says, well, look, the out-of-sample predictive performance of these models, if that's bad, then you can't conclude anything, right? First, you need to have a model that predicts well. Then you can try to interpret it, right? But of course, models that predict very well are often uninterpretable, so that's kind of tricky. So that in that kind of setting, you might want like a semi-parametric model or something. Anyway, so that's one approach to analysis, right? It could be a supervised model, like labeled. And now we're doing predictive modeling again, but we're not interested in prediction except as a sanity check that the model is good. We're interested in interpreting the mapping. Okay, so that's one thing you can do. But, so let me just formalize that in terms of decision theory, because I claim that all four pillars are like just different forms of decision theory with different variations of H, O, pi, and L, and A. So here, this is the generic formula, minimize expected loss. So what are we doing when we're doing parameter estimation? Well, the action is to predict a parameter estimate, theta hat. The unknown state of nature, H, is the true parameter, theta. And let's suppose we use L2 loss. Then the optimal thing to do is to minimize the posterior expected loss, which we can get from a Bayesian procedure, and that's what this quantity here is, right? The tricky thing is that the loss function is defined in terms of theta that you never get to observe, right? It's just some figment in my imagination. So you're modeling, you're trying to minimize loss with respect to something that you can never actually check in the real world, because the real world never gives you thetas. It only gives you data. So you need to do sort of out-of-sample predictive tests to make sure your model is reasonable. Once you believe your model, then this approach is well-founded. Okay, so that's like parameter estimation. But another thing you can do is to say that each data point itself might be high-dimensional, and you want to allow the input-output mapping might have additional variation that's sort of data example specific, that's not captured by the parameters. So in statistics, these are called random effects. But in machine learning, these are called latent variables. And this is what unsupervised learning is all about in machine learning. So basically, as a simple example, let's suppose you have a pile of data in 2D. You've got a bunch of points. And someone says, tell me something interesting about this data. Okay, well, you could run a clustering algorithm, and maybe you discover there are 3 clusters. Are there 3 clusters? I don't know. It's debatable, right? There's no truth. There's only utility here. So evaluating the quality of an unsupervised learning algorithm is very difficult because there is no true answer. So, but this, maybe you know something about the world and you have reason to believe there are 3 clusters. It matches some prior knowledge, or you can check that a model with 3 clusters predicts futures better than a model with just 2 clusters. So you can compute this clustering with simple things like k-means or other methods, right? If you've got higher dimensional data like a molecule or an image or something, then k-means won't cut it. But then you can use nonlinear dimensionality reduction methods like variational autoencoders that learn the low-dimensional mapping that hopefully is meaningful, right? So you can try to read the tea leaves once again and find patterns in your data. Okay, so this is super interesting area. Lots of applications, especially in the sciences. What's my next slide? Oh yeah, so to represent this as decision theoretically, it's kind of the same as before, except now for every data point x, I have a latent variable z. So I'm subscripting them by n, because there's like n of them. and I want to predict the z's for every variable x, right? So that's like predicting the cluster label for every x, or the embedding for every x. And if I want to minimize expected loss, then the posterior mean is the optimal estimate. So now it's the same as before, except I'm estimating latent variables instead of parameters. And the only difference is like there's n latent variables where there's only one parameter vector, right? Okay, but other than that, it's like basically the same thing. So now the main challenge is what's the form of this probabilistic model that represents the mapping between z and x, and then how do we do the computations? And you know, in the unsupervised learning world, there are many possible answers to that question because there's lots of possible models that we might want to fit. So you can do something like contrastive learning with a black box neural net, and that's sort of generic, and you don't have to think very hard. And maybe you have to think about how to define your positive and negative examples. But what you get out is kind of hard to interpret. It might not mean anything. So in the sciences, there's more interest in building like semi-mechanistic models, where you encode some prior knowledge about things that you know, and then you fit the rest, the things you don't know, from data. So here's a little example of work I did a long time ago with a former student, some biological problem, where you got data like this, which this is array CGH data, which was all arrayed back in 2009. And the goal is to find patterns in this, like some of these blips are meaningful. They actually are causal of downstream cancerous growth in cells. And you want to find the things that are shared as opposed to the things that are sort of random variations. And you can kind of write down, this is like some form of hidden Markov model that's hierarchical. And you can write down some prior knowledge coming from biology, and then you can fit this model, and then you can like read the tea leaves. And if you know enough about biology, you can actually conclude something meaningful and then do a test in the lab. And my former student, who's now head of computational oncology at Memorial Sloan, he did this, right, and discovered new things and got a paper in Nature, and it was a big deal. So in this setting, in unsupervised learning, it's often important to work with a domain expert who can actually interpret your results and tell you if you're on the right track or not. And they might also be able to give hints about what kind of prior knowledge to include. And then as a machine learning expert, you can then solve the computational problem. So I won't go into more detail on this example because it's really old. I want to go into more detail on a more recent example that's a little bit similar in favor. But the data is different. Luckily, the video worked. So this is a project I did with some colleagues at Google and an intern. So we were interested in modeling the behavior of animals in cages. So they were either rats or mice. They're rodents of some form. And they were being given drugs, and their behavior changed over time. And we wanted to track it with a camera and try to figure out if we could understand the differences in the behaviors of these animals over time as a function of disease state and the drugs that they are being given. It's a super hard problem, right? So to get started, we worked on a toy problem where this is our mouse. Imagine it's a mouse moving around, and we're trying to find some patterns in the motion of this dot, right? This is a simplification of the mouse problem. And if you stare at this long enough, then you can see that it's following some sort of trajectory. And we want to come up with like a simple description of the trajectory. We're not really interested in generating videos. We're given videos as input. We're trying to come up with a representation of the world. So we're going to feed the raw video into some model I'll explain in a minute. Then out pops some representation that's kind of like a clustering model that partitions the video into regions, so modes. So this is like the clusters we had before. So we have a cluster where the dot is moving in a straight line. Think about this as like a car on a racetrack. And then it gets to the figure 8, right? And it starts slowing down and swerves around. And then it enters a different kind of behavioral mode. And then it enters the curve around, the swerving mode again. So in this case, it's discovered 1, 2, 3, 3 clusters. Sometimes it discovers 4, sometimes it discovers 2. But the point is it's partitioning this long video into pieces that are somewhat simple, but they're not necessarily linear. So that's what we want to do. How are we going to do it? So we're going to use this model that I flashed up earlier. And this is some mashup between a hidden Markov model and a nonlinear Gaussian state space model. It's a bit of a mouthful. So we talked about nonlinear Gaussian state space models earlier when I talked about common filtering for bandits. So that's what these things are here. In the past, the Z's represented parameters of a neural network. Now they represent the motion of that dot, right, where it is on the racetrack and how fast it's moving. So these are just latent variables. They're real valued. And these S's are discrete latent variables that represent which mode of behavior the system is in. Is it in the straight mode or the curving mode, for example? And in the animal setting, this might be, is the animal sleeping, or is it eating, or is it running, or is it fighting? And then this is like, okay, what is it eating, or how quickly is it eating? Where is it running, right? So these are all the other factors that you need to explain the data. And the data's downstream, right? This is an image or something else. Okay, so this is a generative model, and it's called a switching nonlinear dynamical system. And it's switching because these discrete states jump from one mode to another. And then when you're in a mode, you start doing some nonlinear dynamics when you're in that mode. And then you jump to a new regime. So this is useful for sort of parsing into pieces complicated time series data. And if you write it out, then it's just some joint probability model, right, over data, latent continuous factors and latent discrete factors. And the data generating mechanism is some nonlinear model that depends on the continuous state. The states evolve according to some nonlinear dynamical process. And then the states also switch according to some probability transition matrix. Okay. So this is a sort of well-studied model family. It's very difficult to fit these models. So I'm kind of running out of time. So this is a bit complicated, but it's like I'm just giving you little breadcrumbs to give you a taste of what it's like to work in this problem space. And you either love this and think, oh, this is cool because you like math, or you think, oh, I just want to go back to fitting neural nets. But we use neural nets in this as well, but they're suitably constrained to their appropriate part. So we use neural nets to model the nonlinear dynamics. That was what I discussed before. But we also use neural nets to model the posterior. So someone was asking earlier about using neural nets to emulate Bayes' rule. Well, we kind of do that here. We use this thing called amortized inference, which is learning an inference network to represent the distribution over the unknowns given the data. Because we could apply, in fact, it would be a cool project, actually, to do the sort of low-rank Kalman filtering kind of thing that I talked about to estimate these latent states. And I think Ulrich, who's in the audience somewhere, has studied exactly this. So there's a lot of related work where you can use deterministic algorithms to estimate these things. But we use a neural net to estimate the continuous states. And you can fit these kinds of inference networks using gradient descent. But it only works if all the variables are continuous. And this is a hybrid model with discrete and continuous states. So it kind of breaks the standard methodology. So the key insight of our paper is that the discrete states can be marginalized out analytically using the forwards-backwards algorithm, which is a closed-form dynamic programming method. So if you know the z's, which you can get by sampling from your inference network, then these become observed variables. So conditional on the z's, the s's can be collapsed out. So then we get rid of these discrete variables, and we can compute, we can fit this inference network using gradient methods, and then this is just a closed-form algorithm. So that's the trick. And then, so what we do to fit it then is like we optimize the elbow, which is this collapsed marginal likelihood term that we get with forwards-backwards, and then we compare it to a sample from the inference network. And then we also have to regularize this problem. I talked a bit earlier about how many states does it discover. Is it 2, or is it 3, or is it 4? Actually, one of the problems is that it usually picks one state, because the neural net can model everything, and then it doesn't want to change. It says, oh, I can do everything. And we don't really want that from an interpreter. So that's called mode collapse. So if you fit the model, you've got one really complicated neural network that says, I can explain all of that with one neural net. Okay, that's great for prediction, but it's not good for interpretation. So we force the model to use a small number of simpler models. And we do that by adding a maximum entropy term that encourages the distribution over states to be uniform, so it uses all of the states. It doesn't collapse to a single state. And then there's some tuning parameter that we have to set, which is kind of annoying, but you need to anneal that. So if you do all of that, and you apply it to our little demo, then what you get out is something like this that I showed earlier. Sorry, you get something like this. Prior workers considered a similar model family, but used linear models. And they tend to over-segment because each segment has to be linear. And so it gives you too many pieces. So this is like a happy middle ground where it's like a set of pieces, but each piece is nonlinear, or potentially nonlinear. Okay, and then we applied it to various data sets. There's that 2D tracking. There was some Reacher data set, a DeepMind Reacher data set that we applied it to. It's like a robotics problem. And then this is another one where it's motion capture, so it's like 80-dimensional data. And if you watch this video for a while, you can sort of convince yourself there's like 3 modes of behavior. So basically they're spinning, their partner dancing, right? But they don't show the partner. So it's just one person. So they're holding hands, and then don't expect me to do salsa dancing on stage, but you can kind of see, right, that I don't know what this is called, but they're moving in place, and they're about to do a swing, which they will in a second. And they're facing this direction, and then they're going to swing back. And the model, like, discovers that automatically. It discovers some set of states. You have to sort of go in and read the tea leaves to figure out what they mean. But that's standard for unsupervised learning. Okay. So that was just like a little vignette of some project I've done recently in this space. There's a ton of things you can do, right? I think in general, fitting like interpretable or semi-interpretable latent variable models is super useful in the sciences. And you know, there's a lot of room for innovation here because every problem needs like a different solution. So it gives you a lot of room to explore. But you need to work with an expert, otherwise you don't know if you're wasting time or not. All right. I can take a quick question on latent variable models before I move to the final pillar. Everyone wants me to get to the final pillar because they know that synthesis is just...
Please, I have a follow-up question on the... I'm here.
Oh, yes.
Yeah, please, not on this, on the analysis, on the control.
Okay.
You mentioned that you haven't studied the C in your model. You rather concentrate on the updating of the function. So I want to know how you choose the C. Then if you haven't studied it, what are some of the ranges and value ranges of the C that you use?
Yeah, that was asked earlier. I don't know, actually. I mean, I think there are bounds, like regret analysis bounds that are stated in terms of C. So the larger C, the more optimistic you are. So that's going to trade the degree to which you trade off exploration and exploitation. So I think, like in practice, people use some smallish number. I don't know, because I don't know too much about UCB, to be honest. Like I said earlier, we were primarily focusing on the Bayesian updating, and then we just plugged it into UCB. UCB is like something we took off the shelf. And then in Thompson sampling, which I'm more familiar with, the analogous quantity to C is like the prior variance and how you update that, right? So you can use empirical Bayes, or you can treat it as a tuning parameter and do. You can't really do cross-validation in an online setting, but in papers people do that anyway because they cheat. But in the real world, you could do, like, I would do hierarchical Bayes over that. Okay, but let me move on to the final pillar. So synthesis. So this is just data generation, and it's more commonly called generative AI. And this is, of course, super cool, and it's the latest hot thing. And this includes things, systems that can generate text, like ChatGPT and Google's Bard, and can generate images, maybe in response to text. But it also includes, things like weather forecasting, where you're generating high-dimensional outputs. And so we can represent this as a decision theory problem as well, right? So the setup is the following. We are given the unknown world state is like, what should the output be, right? What is the image I should generate? I don't know, right? What is the data that I have? Well, I'm given some prompt or conditioning signal C. So I'm given, let's do an example, a Shiba Inu wearing a beret and a black turtleneck, right? So that's what C is. It's a piece of text. I also have training data, which is created by humans, which is text-image pairs that I scrape from the internet, or I pay people to generate for me. So I have my training set, I have a prompt, I stick it into my policy. What's my policy? It's just the data generator. But this time, instead of predicting a single output, I'm going to sample a set of outputs. And so the difference from prediction is that it's a many-to-many problem. It's not a many-to-one problem. So there is no unique answer. There are many possible images I could generate. And they're not all equally good. Some will be better than others, but there's like many reasonable answers. Whereas in prediction, you're assuming there's a true answer, and if you don't get it, you're punished. here, like, there's a set of possible answers, and they're more or less reasonable. So how you quantify that is in terms of the loss function. So to make progress, we need to specify what this loss function is. How do we know that what we generated is good or not? And then we need to specify what's the form of this generative model. Okay, so let's talk about the loss function first. So let's consider text-image generation, right? So I give you a prompt, toilet paper with real cactus spikes, and you get this out. Okay, how was this done? This was done using the Imagen system, which is a system from Google that I'll explain in a few minutes. But there's lots of other systems that do things like this. Okay, so you get this out, and what's the loss? I don't know. It's pretty good to me. I mean, it's super cool, actually. But you could have another image that like didn't have the spikes, and how do you compare it? It's not really clear what the loss function should be here. So this makes evaluation very difficult, and it's quite subjective right now. If you're training your model or hyperparameter tuning, it's really difficult because like you don't know how to measure things. And same thing in text, right? So I was on a safari actually last week in Tanzania, and I was talking to my tour guide, and he hadn't heard about ChatGPT. So I showed him, and we're saying, okay, what would be a cool thing to ask it to do? So we said, okay, how about write me a rap song about the Serengeti in the style of Jay-Z? So we plugged it into ChatGPT, we plugged it into Google Bard, and they gave different responses, of course. And I'll let you read this offline, and you can decide which one is better. I'm not allowed to say because I work for Google. But I'll let you, you can probably pretty quickly decide which is better. This is with the public version of Bard, I should mention. I didn't evaluate the internal one. Okay, so evaluation is tricky, but like, sometimes it's kind of obvious what's good and what's bad. There are nuances, but like, anyway. So the second problem then is the modeling problem, right? How do we generate these samples? How do we generate these images? How do we generate this text? And that's the fun part. Okay, well, there's a ton of different methods, many ways of doing this, right? I call this the generative modeling zoo. So there's at least 6 major families. And I have a chapter on each one of these models in my book. And I only have 6 minutes left, and I'm not going to do a chapter each in 6 minutes. So I'm going to just pick on 2 very quickly. So one of them is autoregressive models built on transformers. So probably you all know about transformers. If you don't, you need to know about transformers, but I'm not going to tell you because I don't have time. And luckily, my colleague Nando De Freitas is giving a tutorial on transformers on Thursday, so you can just go to that and learn all about it. So I'm off the hook. A second major model family, especially for the image generation, is diffusion models. And the basic idea is the following. So it's pretty hard to generate images from noise, but it's pretty easy to generate noise from images, right? So you can take an image, and you can just add Gaussian noise more and more and more, and you can destroy the signal. And if you do this slowly enough, then you can imagine training a neural network to gradually undo it. So go from here to here, here to here. So learning a sequence of small denoising steps is much easier than going in one step from noise to image. So you can train a neural network to gradually denoise this. And once you've done that, you can just chain these things together, and then you've got a diffusion model. And that is like state-of-the-art for image generation. But that's all I have time to say. It's like a bit too complicated to go into in the remaining time. And I was originally going to do like a deep dive on this, but then I realized that Kevin Eloff, I don't know if he's in the audience. Anyway, he's giving a tutorial on this topic later in the week. Kevin, so you will explain to everyone about this cool model family, so then I don't have to. So, okay, so now I can wrap. These are the 4 pillars I talked about. So, as promised, they're all special cases of decision theory, where I'm changing the world state. So for prediction, the world state's the unknown label. The observation is the input and the training data. The policy is the predictor. The action is the predicted label. And the loss is like 0-1 loss or L2 loss or whatever. Okay, so that's prediction. Then there's like decision making. So there's some unknown world state. And then the observation is maybe you see the state, maybe you get partial observations in the state and some history. The policy is take an action. What action should you take given the current state and the past? You pick the action, and then the losses, like the sequence of rewards or losses that you get over time. So that's decision theory, or sequential decision theory. Then analysis the hidden state of the world is like the unknown cluster label or the unknown parameters. The data that you get is the data vector X and the training data. And then the policy is to predict the latent variables or predict the parameters. So the action is like latent variables Z hat. And then the loss is maybe L2 loss. So that's like data analysis or latent variable modeling. And then synthesis. So the unknown state of the world is like, what is the right rap song to generate? And then what do I observe? Well, I have the text prompt from the user, and I got training examples. And then the policy is some stochastic generator. And then the action is a sample. And then I have some magical loss function, which is like gut feeling of the audience, which they like best. So they're the 4 pillars. That's like 80% of machine learning. But it's not 100% of machine learning. So what have I left out? Like there's the iceberg here. This is all the stuff underneath the 4 pillars that are sort of orthogonal to the 4 pillars. So themes that are cross-cutting and apply to all domains, right? So optimization algorithms. So I mentioned, a few times, I mentioned EM, actually, I mentioned SGD, I mentioned dynamic programming actually in the context of forwards, backwards, right? But there's other optimization algorithms, right? So this is needed for all of those pillars. And then Bayesian inference, I mentioned variational inference and other methods, but like there's a ton of algorithms there as well, right? And that applies to all of these pillars as well. And then there's other things that I don't, so I talk about these, especially inference a lot in my book. There are other things that I don't know as much about, but are also important, like systems issues. So scaling, hardware, and distributed computing, things like that. Automatic differentiation, probabilistic programming languages, DSLs, all of that kind of stuff. Core computer science, that's again like orthogonal to these pillars. And then there's like issues to do with data, right? Where does the data come from? Is it leaking user information? Is it ethical to scrape data from the web? Is there bias in the data set? How do you present results to a human, right? There's all of those issues that, I'm not an expert on, so I didn't really address. So these pillars cover a lot, but they don't cover everything. But hopefully this gives you a bird's eye view of machine learning as I see it. Okay, thank you.
I think we maybe have time for one more question. Does anyone want to ask one more question?
Thanks for the nice presentation. So my question is with respect to the algorithm you explained where you were using Thomson sampling for the decision making, and then you had that new method for doing the model update, where you have your model is like non-linear. So in that case, you consider the contextual bandit setting. Do you have any intuition of how that model will work in the full RL setting? It seems like you can still apply the same method, just change the loss. Instead of it being the reward, it could be like maybe the GQN loss or something else. What's your intuition on that?
Yeah, so you can, we tried that. So it's obviously natural to use the Bayesian machinery on top of model-based RL. We didn't get very good results in like continuous control problems, mostly due to model mismatch. So like if it's a continuous control problem and your predictor is wrong, then the errors compound as you roll forward. So the thing about bandits is like it's a one-shot decision problem. But in RL, like you have to roll forward over trajectories, so errors compound. So it's a much, much harder problem. And we ended up like being Bayesian about the policy, so we did like policy methods instead of model-based, which is kind of annoying. Like there are certainly people working on model-based RL. And I think with more effort, this machinery might help there, but our first attempt failed.
Thanks. And maybe let me just add a quick additional question, because there's also this, it seems similar but tangent idea, which was proposed by Mark Diesendorf like a while back, Pilco, where he uses like a Gaussian process kind of like approach to kind of like model. But in that case, he's in the full reinforcement learning setting. I'm not sure if what will be in your in your kind of like perspective the kind of key insight difference between this approach you propose here and something like Pilco, where he uses like a Gaussian process to model the dynamics and update offline.
Yeah, no, I love the Pilco work. So Pilco, for those who don't know it, it's RL, where model-based RL, where you use a Gaussian process to model dynamics, and maybe the reward, or maybe the reward's known. The issue is that Gaussian processes become more and more expensive as a function of training size. I mean, there's a whole community that works on efficient approximations, but we are tackling a parametric model that's cheaper to update. So, like, in principle, the approach we have could scale to like millions unended streaming data, whereas it's actually an open problem how to do GPs on streaming data. So Pilco is sort of a more of an offline setting with like very small samples, like 20 examples. So, and you have to learn the kernel as well. So whereas this, it's a neural net, we apply it to images. It's not so straightforward to get good results with GPs on images. You can, but it's not easy. I'm surprised there's so many questions on the Thompson sampling stuff. I guess I spent a lot of time on it. But any other questions?
Yeah, thank you. Yeah, it's me.
Hi.
Hi. Hi, thanks for the talk. So I also had a question about the decision part. And so you talked about the EKF algorithm and how it's expensive because of the matrix inversion process. But it seems like the algorithm that you laid out in one of the slides also had matrix inversion. So I wasn't really quite sure where the optimization gain is from in your method. So I wanted to ask about it.
Yeah, let me see if I can find the slide. Yeah. So, so the trick is that we make whoops. So we assume the precision matrix is diagonal plus low rank, so rank L. And given that, you can apply the matrix inversion lemma to compute the posterior using time that costs, it's quadratic in L instead of cubic in D. So it's much more, cubic in the latent variables. So it's much more efficient. The problem is that after you do an update, it's no longer low rank. So then we do an SVD step to make it low rank again. And this is just picking off the top L singular vectors, so this is pretty efficient. You could do a randomized approximation as well, which has been done in prior work, but we want it to be fully deterministic. It's about a factor of 2 slower than SGD. But yeah, the trick is matrix inversion lemma.
Okay, yeah, unfortunately we don't have any more time for questions, but Kevin will be here for a few more days, so if you have any more questions, please reach out to him. Let's give another round of applause for Kevin's excellent opening talk. Okay, and now tonight we will have, coming up next is the opening party. When I asked where is the location, they told me if you go outside and you hear music, just walk towards the music. So it's at the Quadrangle. I think it's a 3 minutes walk from here. If you are staying in the Pentagon hostel, I think there's buses going from the Quadrangle to the Pentagon hostel between 10 p.m. and 11:30. So if you want to know what time to go back, and it's up to you if you want to go to the Pentagon hostel now and then arrive at the opening party. But I think that is all for today, and hope you all have a great first day of the Indaba and have a great time at the opening party. Thank you.